motion. I got motion. What? Why does it keep, you have like a wet dribble of where it goes every time.
Okay. First lesson, like I told you, chapter 1 is a lot about just kind of the basics of a lot of different things that we've done in algebra. And so a lot of this stuff, for the most part, will look pretty familiar to you. I'm going to kind of introduce you to a few new terminology things today. You've seen some of these things in some shape or form probably, and others will be written a little bit differently. There's a couple of symbols that we haven't ever used before that I'm going to kind of introduce you to today as well. Before we get into some of that stuff, I'm going to talk first of all about types of numbers. This is something probably way back when that you talked about the different sets of numbers, types of numbers, how they are all a little bit different, and we put them in different sets. And what I'm going to show you here is, first of all, I'm going to show you the names of them, but then we're going to put it like in a grouping or in a set to kind of show you how they all kind of go together. And then we're going to use these types of numbers to kind of answer some questions today, and I'll kind of show you what that looks like. So first up, real number, okay? These are your sets of numbers. So a real number is any number. You tell me a number and it's a real number, okay? That includes even things like pi or radicals or anything, okay? Any number you can tell me, it's considered to be a real number, okay? Back in Algebra 2, you might remember imaginary numbers. The good thing about intermediate algebra is we don't ever do imaginary numbers. So you guys are probably disappointed by that, right? The good old imaginary numbers. Don't have to worry about that. Okay, so now what we're going to do is we're going to break it down into some different categories. So first category is, and I'm going to use a letter that represents each one of these. So real is always R. Okay, real numbers is R. And we'll use those letters as ways to identify that set of numbers. Rather than writing out the word real or rational, we can use letters to represent that set of numbers. A rational number is represented by the letter Q. Because we already used R for real number, then we got to use R. We can't use R again, so we use Q. I imagine it's because it's so close in the alphabet to R. I don't really know why we use Q. Sometimes I get that question. Just the letter that we've always used for rational numbers is Q. All right. Looks like we got a fire drill. So we're just going to go down the stairs by Mrs. Heron's room and out by the ag room.
You're making me very sad. You're making me have hard thoughts. Girl. What? I'm trying to see what time. 10:18. No. What? Yeah, yeah, 10:18. No, you got it. Yeah, I did. What? Stop. Well, good thing me and Clea got to our seats first. Okay. Technically, I got to my seat first. This is some precious stuff. Technically, I think you should. Oh, wait. You're also good too. Okay. Well, you know you can't be right or ruler. You'd rather be by me.
Hey, next to each of these definitions, I'm going to put this box, and this box is going to represent each set, and it's going to show you kind of how all of them kind of are represented together and how they all kind of work together. So this box, this whole box, anything that goes in this box is a real number. So we already said real is everything. So everything in this box is a real number. And then we're going to break it up into two parts. So the first one is rational. What is a rational number? Anybody want to take a guess, or anybody remember what a rational number is? What'd you say? It could be decimals, okay. Sometimes it could be a decimal. What about a number like 8? Rational?
Yes.
Sometimes. Yep, eight's rational. Yeah. Could be a decimal. What did you say? Could be an even number. Yeah. Okay. But there's a definition that we use for rational numbers that will include all those things that we just talked about. Anybody remember what it is? Any number written as a fraction. Okay, so I mentioned 8, right? 8, I could write 8 as like 8 over 1 or 16 over 2, right? Just different formats of 8. Typically don't write it like that, but we could. Kingston mentioned decimals. A number like, hey. What do we got?
Are they just college?
Oh, college check. Yeah, just call my account. Awesome. Thank you so much. Like 1/3. Okay, 1/3 is typically written. We could write it as 0.3 repeating. We could also write it as a fraction. So sometimes we write it as a fraction. Sometimes we write it as a decimal. So we have a whole long list of things that could be rational numbers. Okay, and we use the letter Q that represents that. So when I do my box over here, I'm going to put Q in this side. And I split the box up into two parts. And I didn't necessarily do it evenly because most numbers that we're familiar with are rational. But then we have irrational. Irrational, we use an I. Since it starts with the letter I, we'll use I for irrational. So then it would be just the opposite. It would be any number that we can't write as a fraction. There's not as many of those. So what is a number that we are familiar with that can't be written as a fraction? We could write 0 as a fraction. We could do like 0 over 2, because 0 over 2 is really still 0. Think of some numbers that you've been exposed to in different classes that we're familiar with. Pi. That's a good one. Okay? Because what do we know about pi? It's infinite, right? It goes on forever. Does it repeat? No. Okay? Because it's a decimal, and because it doesn't repeat, it just keeps going on forever, there is no fraction that represents pi. Okay? And so pi is a great one. Okay? Another one would be a number like radical 7. Radical 7, if I put it into my calculator and take the square root of 7, I get this big long decimal that keeps going on forever. Now your calculator will take it out to like maybe 10 decimal places, right? But it does keep going on forever. Your calculator just has to stop at some point, kind of like pi. We know pi goes forever, but my calculator only can take it out to so many decimal places. So those would probably be the two most common examples of where you would see an irrational number, but there's not very many of them. Okay, those are probably the two most common that we would see. Okay, so if a number is irrational, once we determine that it's irrational, then that's it. That's the only other set of numbers that it belongs to. But if a number is rational, then we can go further. Integers. Okay. Integers is a pretty common term that we've seen throughout some of our different math classes. Integers are your positive and negative counting numbers, but no fractions. Okay, and so I'm just going to put it in a list here where I'm going to say -3, -2, -1, 0, 1, 2, 3. And it's going to continue in both directions. So those dots just means it's going to continue either way. So we're not talking about fractions or decimals when we talk about integers. We're just talking about positive and negative counting numbers, including 0. The letter that we use for integers, we already used I for irrational. So the letter we use for integers is Z. Once again, why do we use Z? Not really sure. I think it's just because it's kind of an uncommon letter, and so Z is what we choose to use for integers. So it is what we call a subset of rational numbers. So I'm going to put Z in here. All integers are rational. So all of these numbers here are rational numbers. Okay, so it's a smaller set. We're taking out fractions. Fractions are not part of that set. Okay, we got two more sets. The next one, whole numbers. Whole numbers, we use the letter W. Okay, and we're going to keep getting a little bit more specific. Okay, so integers were all your positive and negative counting numbers. Whole numbers, anybody want to take a guess where whole numbers start at?
1.
Not quite.
2.
Other direction.
0.
0. Yep. Starts at 0. Okay, I always remember whole, but it has the O in it. Okay, whole and 0 kind of reminds me of where it starts at. So it's all your counting numbers starting at 0. It takes away all your negatives. So whole numbers are a smaller subset of integers. And then the last one is the numbers that we used like way back when we learned to count and those are what we call our natural numbers. So we just call these our counting numbers. So when we started counting, we probably didn't start with 0. We started with 1. Natural numbers, we use n, and the only thing that's taken out of the mix here is 0. Okay, so we just keep getting a little bit more specific. All of these are types of rational numbers. So, for instance, if I said a number like, here's what we're going to see on some of these problems. If I gave you a number like 8 over 2. Well, we know 8 over 2 is really 4, right? We might express it a little bit different way, kind of like sometimes I can express a number as a decimal, sometimes I can express it as a fraction. I can say 8 over 2. Typically, we don't leave it as 8 over 2. We say it's really 4. And if I said, what sets of numbers does it belong to? Okay, basically, you're going to go one or the other. It's either got to be rational or irrational. Okay, and even more specifically here, we can say that it's natural. Well, if it's natural, then it's also a whole, an integer, a rational, and a real. Okay, and here's where we use the letters. We could simply just say real, rational, integer, whole, and natural. Okay. And here's what I'll tell you is because all numbers are real, then typically we don't really say real, even though we could put that for every single set of numbers. If you don't include real for right now, I'm okay with that because all of the numbers are going to be real. So we already know that's going to be included. So really we're just looking at inside of the box, real, rational or irrational, and then does it belong to any of the smaller subsets. Okay, so if I looked at a number like -9, is -9 a natural number? Nope. Is it a whole number? Nope. Okay. I'm going to keep working my way up. I kind of start inside out, basically. Is it an integer? Yep. Okay. And if it's an integer, then it's also rational. So -9 would belong to rational and integers. And those would be the two sets. If you said real, that's fine, but I'll just say we don't need to say real because all of these numbers will be real. All right, so where are we going to use some of these things? We're going to talk about types of numbers a lot, and you'll hear some of these more than others as you go through any algebra class that you take. When I talk about whole numbers, less than 4. Okay, and I ask you to express that out. There's a couple of different ways that can happen. And the reason we have a couple of different ways is because in some ways we could do it in a list. And when we do it in a list, we call that roster notation. Okay, so we're going to make a bracket, okay? And what is a bracket? It's just a symbol, and mine kind of just looks like a squiggly mark, really, but it doesn't have to be anything special. But it's just a set or a symbol that encloses that set, okay? So that would be a bracket. And so if we talk about what numbers would belong in that set, what whole numbers are less than 4? Well, whole numbers start where? 0, okay? So we're going to start at 0, and then we're going to go 1, 2, 3. Do we want to include 4? No, because it's got to be less than. If it said less than or equal to, we could include 4. So 3 would be the last number, and that would be my set. We're just going to list them out, okay? We call it roster notation because you're going to list everything that's in that roster or in that group. It's just the terminology that they use. Okay, this next one, and this is something, if you take algebra or college algebra later down the road, we use this notation a lot. We didn't really use this notation much in Algebra 2, or maybe at all in Algebra 2, because it's not really something that we do a lot of in Algebra 2. The reason we have this notation is because if my set is really large, this would just be another way that I could say it or write it out. Okay, we still use the set notation. And we're going to say all values of x such that x is whole number less than or equal to 4. We don't just want to say less than or equal to 4, because then that would include negatives and things like that. The whole number is a big part of what we want to say. And sometimes we can do it in words, sometimes we could do it in symbols. I could say x is less than or equal to 4, but once again, I don't just want to say x is less than or equal to 4, because that would include negatives and some other things that we don't want to include. Okay, so that's kind of the difference between those two sets. We could list it out, or we could just write it out as some type of terminology. The reason why this would be better, if I said whole numbers greater than 4, well, let's just talk about that real quick. I'll just do it right next to it. And let's do integers. Greater. And I'll just do a different number here. Greater than negative 4. Integers greater than negative 4. Okay. For roster notation, that's a little bit harder, right? Because that list is going to go on forever. So if I was going to do that in roster notation, I would say negative 4, negative 3, negative 2, negative 1, 0. You could include 1 in there, but we're just going to keep going up, okay? And once again, those dots just means we're going to keep listing that out forever. There is no end, there is no stop to it. If I did this as set builder notation, I would just say x, and I always use x because that's just the variable we use for algebra most of the time. You can use a different variable if you want to. And we just say all values of x such that x is an integer greater than 4. And so you can use your greater than, less than symbols here if you want to. Kind of eliminates having to use words. Negative 4, sorry. Got the negative. Okay. So listing it out versus putting it kind of in words is the only difference between those two. Or symbols, using symbols. Okay, if I said natural numbers less than negative 2. Okay, where do natural numbers start at? 1, right? So what natural numbers are less than negative 2? Nothing, okay? And so there's a couple of different ways that we could write this. We could still use the symbols, but what we're saying here is that this is an empty set. There is nothing in that set. Nothing belongs to that because there is no numbers that are natural that are less than negative 2. Another symbol, you might have seen this before, is a 0 with a slash through it. It means there is nothing in that set. We call that a null set or an empty set. A lot of different words that you might hear called. Just, it's nothing there, okay? nothing belongs to it. Now, I will also tell you too that there's going to be some examples where I'm giving you examples that are math-wise. I think some of the problems that you're going to see on your assignment today are going to give you maybe some real-life examples that you're trying to do a roster set versus a set builder notation. If I said months beginning with P. Months beginning with the letter P. So if I said, what months do we have that start with the letter P? We could go all through all 12 months and we would find out that nothing fits it, right? And so that would be another example of an empty set. Okay, there isn't anything that fits that. So it could be math related. It could be an example that may not be math related. Just so you know that you're going to see some things like that, and you might say, well, how does that fit in with the numbers or the other things that we're doing? It may not. It's just, if I said months starting with the letter A, I would list out the months starting with the letter A, August, April, and that would be my roster notation. But if there isn't anything, then it would be an empty set. Okay, some vocab. These are words that we will use all throughout any algebra class, really, okay? And so these are all words that I think you have been exposed to at some point in time, probably many, many times, in fact. Variable is a big one, okay? When you first started taking Algebra 1, and we said, well, what is X? And you looked at X, and you're like, now we're going to use letters for math? Great, right? I thought letters were for English and vocab and all that. Well, when we do variables in algebra, it is any letter that represent a value. If I was doing a story problem, I might use A for apples, just because A is going to tell me that I'm solving for apples or I'm looking for apples or whatever it might be, okay? If it's just a normal old equation, we typically see X or Y or N or some other variable. But we've seen variables a lot. We'll solve for those variables. It's just representing a value. Hey, if I think of the word constant and what it means, constant just means to remain the same, right? It is not changing. So what are some things in math that remain the same, don't change? If I said the number 2, will the number 2 ever change? Nope, number 2 is always 2, right? It's never changing because there's nothing else that represents it. It's just 2. We know what 2 is. We know how to count 2. That is an example of a constant. A constant is just a numerical value. Any number, okay? 2, a half, anything, it could be a decimal. It's a numerical value. That numerical value always remains the same. It doesn't change. We know its value. When it's X, we don't know what X is. X could be 2, X could be 8, it could be anything. Okay, an expression is a combination of a constant and a variable. Usually with some type of operation included in it, but there wouldn't necessarily have to be an operation, but typically there would be. So here's some examples of expressions. And I'll just say, here's some examples. So 2y would be an expression. 2 would be my constant. Y would be my variable. In this case, if there's nothing between them, we know we're taking 2 times y. So there's an assumed multiplication there. I could say n plus 6. That would be an expression. We don't know the value of n, we do know the value of 6, so that would just be an expression. And we could put any operation in there along with that. I could say b over 4. I could put subtraction in there as well. And there could be more than one variable. I could do something like 7 ABC. And so I'm taking 7 times A times B times C. If I was going to evaluate that expression, then I would need to know the value of A, B, and C. And that will be something that we'll do later on in the chapter, is evaluate expressions and knowing what the value of A, B, and C are, or being given the value of those. But it's just a combination. And there's a lot of different ways those expressions can be written. Okay, equation. What's the one symbol that we would add if we have an equation? Equal sign. Yep, this kind of is the giveaway, right? Equation has an equal sign. So it's simply an expression with an equal symbol. So I could say x minus 4 equals 12. Okay. Eventually we'll solve that, but right now we're just saying that would be what we call an equation, because now we've added the equal sign to it. We're saying that these two expressions are equal to one another. They're equivalent. Okay, and then inequality. Once again, very similar definition here. It's an expression with an inequality symbol. Your 4 inequality symbols that we're familiar with: less than, greater than, less than or equal to, greater than or equal to. Every once in a while we might see this one, and it's still called an inequality symbol. It's an equal sign with a slash through it, and that just means not equal to. Okay, it's not an equation. It's something other than an equation. So I might say x cannot equal 5. Okay, and so those two would not be equal to one another. Okay, a prime number. This kind of goes in a little bit different direction. But if I have a prime number, anybody remember what a prime number is? Close. 3 is a prime number. So those would be multiples. Like 3, 6, 9 would be multiples of 3. 3 is...
like one way to get to the number. One way to...
Okay, so 3 is a prime number. What would be another example of a prime number? 7. 5.
So odd numbers.
Okay, could be. Is 9 a prime number? No. How come? Divisible by 3. So a prime number can only be divisible by 1 in itself. Okay, one last symbol here, and then I'll put the assignment up here. There's a few things I didn't get to, but we can kind of clean those up tomorrow. This is a symbol that we haven't seen before. The way that we read this is a subset of. So I could say whole numbers are a subset of rational numbers. Okay, and we could go more specifically, but that's how we would read that. Whole numbers are a subset of rational numbers. And we could make it a little bit more specific. Okay, because of the fire drill, there's a few other things I want to get to. I'm going to put the assignment up here. Now, I will tell you up front, when I write this out here, and I will put this on Classroom today as well, so if you don't get this all written down, like I told you, there's a ton of problems in here, and early on, a lot of these problems don't take a lot of time, so this looks like a lot of problems, but most of these are just look at it, answer, okay, and really aren't that bad. What I will do is I will post a video of our lesson, and then in the notes of the video or in the assignment post, I will have the assignment problems. So if you don't get this all written down, it'll be on Classroom at the end of the day as well. Okay, looks like a lot. So here's your page numbers. Here is, and sorry, this is also even right here, 38 to 50 even. I forgot to write even on that. I will get that in Classroom for you. Okay, there'll be a few things on there that we didn't get to today, so if there's something in there you're not sure about, I'll kind of clean up a few things tomorrow because of the time that we had today.